Hello, and welcome to my video project for Chapter 5. In this long and difficult chapters, we learn many things. Through this video, I have focused on the most fundamental parts we learn that can sometimes be the easiest to forget. Ready to start? Let's begin. In the first part of Chapter 5, we learned about the differences between mixtures and pure substances. A mixture is composed of two or more elements, while a pure substance is made up of one element. But words are too confusing, so let's look at an example. In a salad, we have lettuce, croutons, tomatoes, and some carrot sticks. That's a mixture that we think about, and we have these in our everyday lives. When we mix it, another example we can do is water and salt. When we mix the two together, and we stir it together, we get salt water. We learned ways of separation. In order to separate salt water, we could use a distillation apparatus, we could filter it, or we could strain it and separate by size, but that doesn't really pertain to separating salt water. An example of a pure substance would be a gold ring. When purchased, the jeweler told my mom that this ring is 100% gold. This can mean two things. A, either the ring consists entirely of one element, gold, or B, my mom got ripped off. Let's assume the first option is true. The ring consists entirely of gold and no brass or other types of elements are here. Also, we learned about chemical and physical changes in this chapter. Chemical changes involve a change in the arrangement of atoms in a compound. Indications of a chemical change include a change in color, production of a gas, and absorption or releases of energy. A physical change, on the other hand, involves a change in the size of a thing. We found in the lab we recently did that adding white powder was a chemical change, since the mixture changed color, and the physical change was when the blue rock got smaller as they entered the mixture. Okay, the next part of Chapter 5 we learned involved compounds and chemical bonds. We learned about covalent bonds, which refers to the sharing of electrons. Okay, here's a way to think about it. Pretend we have a Snicker bar, or pretend we have two fluorine atoms. The Snickers bar is going to be the electrons in between them. If two fluorine atoms want to have a covalent bond, they're the same size and shape, as shown by this picture right here, fluorine. If they're the same size and shape, they're going to both try and grab the electron, but the two will never get it to spend more time with each other. Goes back and forth. However, if we were to have a different molecule, such as H2O, the oxygen atom here is much bigger than the two hydrogen atoms. Thus causing the electrons to spend more time with the oxygen than the hydrogens. This is due to the fact that oxygen has higher electronegativity. Okay, got it? Good. Alright, the next part we learned was about ionic compounds, or the transfer of electrons. Here's a classic rookie example. Sodium, Na, is composed of salt is composed of sodium and chlorine. Sodium has one valence electron, and chlorine has 7. Now, chlorine would be happy to have 8 valence electrons, and sodium would be happy to have none. So, the sodium transfers its electron to the chlorine, thus giving it a +1 charge, and chlorine a -1 charge. Now that we understand these two types of bonds, let's learn about the Lewis structures. The Lewis structure is actually what I just did, and it's also called electron dot diagrams. Let's do a practice example, and then you can try one yourself. Ci4 will be the first example. Ci4. Okay, so we have 4 iodine atoms, and we have 1 carbon atom. So, carbon has 4 valence electrons, 1, 2, 3, 4, and iodine has 7. Now, carbon can donate electron to each of the 4 iodine atoms. So that their energy levels are filled. And carbon now has a +4 charge. So we'd write this, C +4, iodine -1, and there are 4 of the atoms here. Okay, ready to try one for yourself? Let's give it a whirl. We'll do pH3, which consists of a phosphate and 3 hydrogen. Phosphate has 5 valence electrons, and hydrogen has 1, of course. Here's what it looks like. Remember the rules I just taught you? I'll give you a minute to think about this. All good? Alright. What we can do here is have each hydrogen atom come over to the phosphate, thus giving phosphate 8 valence electrons, and hydrogen, all 3 of them, with +1 charges now that they lost their electrons. So we write that P -3, H +1 for 3. Thank you for watching today's video. I hope you enjoyed. Goodbye.